When we study linear algebra, we often ask how a matrix modifies a vector. We can quantify this by looking at the growth factor, which is the ratio of the norm of AX to the norm of X. While eigenvalues are great for repeated applications of a matrix, they often fail to give us a complete quantitative picture, especially for non-normal matrices. Consider a matrix with zeros on the diagonal and a value of 1,000 in the top right. Its eigenvalues are all zero, which might suggest the matrix does nothing. However, if we apply it to a specific unit vector, the output norm jumps to 1,000. This discrepancy shows that we need a more robust tool to measure how much a matrix can actually stretch or shrink space. This need leads us directly to the concept of singular values, which provide the true measure of a matrix's quantitative impact. The singular value decomposition, or SVD, is perhaps the most powerful decomposition in linear algebra because it applies to any matrix, even those that aren't square. It states that any matrix A can be factored into three parts: an orthogonal matrix U, a diagonal matrix S, and another orthogonal matrix V star. Geometrically, this means any linear transformation is just a rotation or reflection, followed by a stretching along the axes, and then another rotation. The diagonal elements of S are the singular values, which are the square roots of the eigenvalues of A star A. These values tell us exactly how much the matrix stretches space in different directions. Furthermore, the columns of U and V provide orthonormal bases for the four fundamental subspaces of the matrix, giving us a perfect geometric map of the transformation as seen in the relationship between the input sphere and the resulting output ellipse. To compare matrices or measure errors, we need the concept of a matrix norm. The most common is the induced norm, or operator norm, which represents the maximum possible growth factor. Interestingly, this norm is exactly equal to the largest singular value of the matrix. Another essential measure is the Frobenius norm, which you can think of as the Euclidean distance if you treated the matrix as one long vector. The Frobenius norm is equal to the square root of the sum of the squares of all singular values. Both norms are submultiplicative, meaning the norm of a product AB is less than or equal to the product of their individual norms. While the induced norm tells us about the worst-case stretching of a single vector, the Frobenius norm captures the total energy of the transformation. Understanding these norms allows us to bound the spectral radius and ensure stability in numerical computations. SVD isn't just theoretical, it's the backbone of data compression and principal component analysis. The Eckart-Young theorem tells us that if we want to approximate a high-dimensional matrix with a simpler, lower-rank one, the best way to do it is to keep the largest singular values and discard the rest. By truncating the SVD at rank K, we create a new matrix that is the absolute closest possible match to the original in terms of both the operator and Frobenius norms. This allows us to represent complex datasets or images using far less memory while preserving the most important features. For example, in image processing, a large pixel matrix can be compressed by storing only the most significant singular vectors. The error of this approximation is simply determined by the first discarded singular value, giving us a precise way to balance compression and quality. When we deal with perturbations or small changes in a matrix, the Neumann series becomes an invaluable tool. It provides a way to express the inverse of a perturbed matrix as an infinite sum, similar to a geometric series for numbers. If we have an invertible matrix A and we subtract a small matrix B, the inverse of A minus B can be expanded into a series of terms involving powers of B and the inverse of A. This expansion is guaranteed to converge as long as the norm of B is sufficiently small compared to the inverse of A. This result is fundamental for proving the continuity of the matrix inverse and for analyzing how errors propagate in iterative numerical methods. It shows us that if our perturbation is small enough, the system remains stable and solvable, providing a bridge between exact theoretical solutions and approximate real-world calculations. Finally, we must consider the sensitivity of our linear systems to noise or rounding errors, a concept known as conditioning. When solving AX equals B, small errors in our data can lead to massive errors in the solution if the matrix is ill-conditioned. We measure this sensitivity using the condition number, kappa of A, which is the product of the norm of A and the norm of its inverse. For the Euclidean norm, this is simply the ratio of the largest to the smallest singular value. Geometrically, the condition number describes how flat the output ellipse is. If the ellipse is very thin, a tiny change in the input can cause a huge jump in the output. High condition numbers often arise when a problem involves vastly different scales of time or space. Understanding conditioning is essential for anyone performing numerical simulations, as it tells us exactly how much we can trust our computed results.